All right, we're going to do chapter 11 all at once. And the first four lessons are broken down here, and all of them hopefully are familiar to you. We're going to get into 11.4 and 11.6 in a little bit. I guess the best way to summarize these four lessons is by the formula sheet that you'll see right here. All of these formulas are pretty straightforward. Most of them you've seen before. I'm going to get into a couple of them specifically. 11.1, rectangles. Maybe you've heard of length times width instead of base times height. But notice that it's the same as the parallelogram because we know that rectangles are parallelograms. So we have that. Also, triangles, half of that. Trapezoids, circles are down here. We're going to get into those a little bit more. I will tell you that in terms of your answers for any circle problem, every answer should be in terms of pi. The only one that I think you might not know or have seen before is the area of a rhombus. And so the area of a rhombus is the formula half of diagonal 1 times diagonal 2. So it's just multiplying those three things together. Those are all formed by using the idea of right triangles because we know the diagonals of a rhombus are perpendicular. And so we're taking the formula from an area of a triangle and we're essentially morphing it into base times height. But instead of base times height, it's the whole diagonal and the whole diagonal. So if you have a rhombus, you can use the formula for a parallelogram, or you could use, if you have only the diagonals, you could use the diagonals in the formula for specifically just a rhombus. All right, we're going to flip through here. Bear with me 1 second. We're going to skip down to sorry. All right, so regular polygons. Regular polygons are obviously polygons that have equal sides and equal angles, and you'll see some examples here. There's a specific formula that's used for the area of a regular polygon. And when I show you the formula, you're going to see the formula and not understand exactly what it means. The area of a regular polygon is equal to half a times p. Well, neither of those are really put into play when we talk about any dimension of a polygon. So the A stands for the word apothem, which we're going to talk about in a second, and P stands for perimeter. Very rarely do we talk about the area of a figure and relate it to the perimeter of that figure. So an apothem is a segment drawn from the center of that polygon perpendicular to one of the side lengths. Now, the reason we do that is because we're also going to be using angles that are formed within that polygon. For example, each angle of a polygon is created by a central angle. The central angle is formed when a circle is circumscribed about that polygon. So if I could take every single polygon that we have, as long as it's regular, I could circumscribe the circle or I could inscribe the polygon, and you would have that. Every time I do that, a central angle is formed by taking the center point of the circle and drawing 2 radii to the outside. This angle right here for a square is 90 degrees. Let me see if I could use straight lines this time. This angle right here for a pentagon, from there to there, and from there to there, those 2 radii form a central angle that is 72 degrees. As you can see, all of these central angles are listed here. Now, with that, the reason we draw the apothem is so that when the angle is drawn, we can now find the area because we're drawing a right triangle, or we're creating a right triangle with the apothem and the side length of the polygon. So if we go back to that, drawing here, we have an apothem. The apothem is created from the center point of the circumscribed circle to the side length as an altitude perpendicular to the side length. And then we're drawing two radii, one on one side and one on the other side of the apothem. And what that does is it creates basically a triangle. That triangle is congruent, basically the number of times that that triangle exists in the polygon. So for instance, in a hexagon, there are 12 congruent triangles exactly like this triangle right here. So I could draw another radius there, I could draw another radius there, I could draw another radius, and so on and so forth. All of those triangles are all congruent. There's 12 triangles that have the exact same size as this triangle right here. 12 of them. So when you think about the perimeter is a six-sided figure, but remember, we only want half of it. So the reason we want half of it is because it's a triangle. That's the formula. So if you know the length of the apothem and you know the side length, then this is a pretty simple formula. Problem is that very rarely do we know either the apothem or do we know the perimeter. We'd have to find one of those two things, or sometimes both. So I'll give you an example. Here's our hexagon. Our hexagon has an apothem of 9. So if we have our formula, we know that the area equals half of 9 times the perimeter. The perimeter we don't know. So we do know that the apothem is 9. Following the steps that I just showed you, we need to draw two things. We need to inscribe the polygon in a circle. Do your best. And in reality, you don't need the actual circle. It's a good visual for you to be able to see that what we're going to do next is we're going to take that apothem and we're going to draw a radius. And the reason we want to draw the radius is so now we can find some information. The first thing we want to find is what's the central angle that's created by a hexagon. Well, if we go back to our chart here, a hexagon has a 60-degree angle created by the central angles of the radii of a hexagon. But if we think about that in more specific terms, if this whole angle is 60 and I just take an altitude to it, that makes half of it right there 30. And so I have this triangle right here that has this is 9, this we're not sure, and this we're not sure, which we don't really need the radius. But the most important thing we found out of the radii of this whole thing is that this angle right here is half of 60, which is 30. And when I know that that's 30, that means that I have a 30, 60, 90 triangle, and the apothem right here is 9. So that's my long leg. It's opposite the 60-degree angle. I know I have to divide 9 by root 3 to get back to this short leg here. 9 divided by root 3 is 3 root 3. Give me 1 second. I have to do a little radical there. 3 root 3. So I know that I have the perimeter is 3 root 3. How many 3 root 3s are there? Well, there's 12 of them. So the perimeter of this figure, this hexagon, is 12 times 3 root 3, which is 36 root 3. Don't forget, you also have to multiply it times the 9 and then divide it by 2 or cut it in half. The fastest way to do that is to take the 36 and divide it by 2. We know that our answer is going to end up with radical 3. We know that because there's no other radicals there. So however you want to do the 9 times 18, that's completely up to you. You could do 9 times 36 first or anything in between. But I'll just do 9 times 18. 162 root 3 is going to be your final answer for the for the area of this regular figure. 162 root 3. Give me 1 second. I can get that out there for you. All right. 162 root 3. And that's how you're going to leave your answer. We don't need to write it in a decimal. We're going to keep it. But sometimes you will need to use sine, cosine, or tangent in your answers to find the missing pieces. You may need to find the apothem. You may need to find the perimeter. You may need to find both if you're just given the radius of the circle. All of those things are fine as long as you know one thing. You know the central angle, and then you cut it in half. Central angle, the apothem divides it by 2. It bisects it. Use those angles, and whether it's using trig or something else, like a special triangle, you can do that no problem to find the missing pieces. All right. Next, areas of sectors. This is 11.6. Areas of sectors. Arc lengths and areas of sectors. In this part here, we're going to talk about not the degree measurement of the arc, not the degree measurement. That was chapter 9. We're talking about as the circumference of this circle is given, what part of that circumference is just the green or just the blue? And all of those numbers, as we know circle graphs to be, are a percentage of the whole. So here are your two formulas. The length of the arc, AB, is measured by taking the circumference and finding out what fraction of that circumference is the sector that we're looking for, or the length that we're looking for. Same thing with area. The area of sector AOB is taking the formula for a circle, pi r squared, as the area, and then finding out what fraction out of 360 degrees is that particular sector. So for instance, if x was 120, 120 divided by 360. The degree measurement is not the length, and the degree measurement is not the area. But the degree measurement is going to tell me what part of that is the fraction of the whole. So in this case, if it were 120, it would be 1/3 of the circumference of the whole circle and 1/3 of the area of the whole circle. So that's how we would find the area and length of a sector of a circle. If we go back to the example, okay, and we'll use simple terms. Remember, we're doing this in terms of pi, So here we're given the percentage. Let's say that the radius of this sector right here, let's say the radius of this, we'll make it easy, we'll make it 10. If the radius were 10, okay, that means the area of the circle would be 100 pi, right? 100 pi. Now I need to find my pi button, which I don't have. There it is. So my area is 100 pi. That also means that my circumference is taking the radius, doubling it pi. So my circumference is 20 pi. Now, 20% of that is just taking this whole calculation and multiplying that calculation by 20%, or 100 pi times 20%, or whatever the percentage is. In this case, we're given the percentages. But if we weren't given the percentages, all we're going to do is take this arc measurement as a degree and make that over 360. Because we're doing it over 360, we're taking that whole section as a degree measurement and just finding the portion that the sector is representing. That is going to be the last section in Chapter 11 that we're going to cover. You can use this information for your packet and continue that work through the week.